Good afternoon, everyone. My name is Leonardo Lamanna, and I am a PhD student of the University of Brescia and the Fondazione Bruno Kessler in Italy. Today, we'll present a work focused on action model learning for classical planning. Firstly, we will give a brief introduction as well as motivations behind this work. Then we will look at how action models can be learned online by executing actions. And we will present the OLAM framework together with its theoretical properties. Finally, some experimental results are given as well as conclusions and future works. So the automated learning of action models is widely recognized as a key and compelling challenge to address the difficulties of the manual specification of planning domains. Most state-of-the-art methods perform this learning offline from an input set of plan traces generated by the execution of successful plans. However, how to generate these plan traces is still an open issue. Moreover, plan traces might not be available for a new or unknown environment. So in this case, we would like to learn action models online. We proposed a method for online action model learning incrementally during the execution of plans. Our method relies on some assumptions. In particular, the set of predicates, operator names, and objects must be known a priori by the agent. Moreover, we assume that there are no negative preconditions without loss of generality, and that there are no inconsistent effects, even if OLAM can be applied regardless of the inconsistent effects assumption, as we will see in the experimental evaluation. The most important assumption is the full observability of both actions and states. So how can an action model be learned by executing action with full observability? Suppose that we start with an action model where for each operator, the set of effects is the empty one, and the set of preconditions is the set of all positive literals involving input operator object types, which can be computed by the algorithm itself. Whenever an action is performed, there are two possible outcomes. Either the action succeeds or it fails. Here it is shown an example of successful action where before executing the action, the operator schema contains the unnecessary precondition at Robbirum y and contains no effects. After executing the action, the precondition at Robbirum y is removed since it is not satisfied in the state where the action has been successfully executed, and moreover, the agent, by comparing the previous state with the destination one, learns the positive effect at Robbirum y and the negative effect at Robbirum x. Here it's worth noting that we are learning the lifted action schema by means of grounded observations, so that the same action model can be applied in different environments. Alternatively, if the action fails, then we cannot remove preconditions or add new effects, but we can identify the preconditions necessary to execute the action, since they are not satisfied in the state where the action failed. Like in this example, where the agent moves from room 3 to room 1, but there is a wall, so the precondition link room x room y is not satisfied, and the action fails. In this way, the agent learns that link room x room y is a real precondition. This is a simple example with only one unsatisfied precondition, but in our method, we also deal with multiple unsatisfied preconditions. However, not all states are suitable for learning, like in this example, where the agent moves from room 3 to room 4, but all preconditions are already satisfied and no further effects can be learned. So in this case, the agent must plan to reach a so-called learning state, that is a state from which some preconditions or effects can be learned by executing a so-called learning action. In particular, in a learning state, it must hold at least one of the following conditions. If the preconditions of an action are not satisfied, then the agent can attempt such an action to check whether these are really preconditions or not. While if there are some possible positive effects which are not satisfied in the learning state but could become true by executing the action, then the agent can attempt such an action to check whether these are really positive effects or not. And similarly for the negative effects. So let's deepen how the OLAM algorithm works. At the beginning, the agent observes its environment status. Next, it computes a goal which can be focused on removing preconditions, confirming them, or adding new effects. Next, it plans to reach a learning state and execute a learning action. Typically, at the beginning, the initial state is already a learning one, so the plan contains only the learning action. Next, the agent selects the first plan action and executes it. If the execution fails, then the agent can confirm some preconditions which are not satisfied. Alternatively, if the execution succeeds, then the agent can remove preconditions or add new effects by comparing the previous state with the destination one. Next, the agent again observes the environment status and so on. The OLAM algorithm stops whether no more learning states can be reached and no more learning actions can be executed. Our method satisfies two theoretical properties. The action models learned are correctly approximate the ground truth ones, that is, given a transition in the learned model, such a transition is also in the ground truth model, and the destination state in the learned model is contained into the destination state in the ground truth model. So in this case, any valid plan for the learned model is also a valid plan for the ground truth one. While a learned action model integrally approximates the ground truth model, if given a transition in the ground truth model, such a transition is also in the learned model, and the destination state in the ground truth model is contained into the destination state in the learned model. So in this case, any valid plan for the ground truth model is also valid for the learned model. We tested the OLAM algorithm on a large set of past international planning competition domains. For each domain, we generated 10 small or middle-sized instances using an available problem generator. Then we ran OLAM from the smallest instance to the largest, and during the first instance, OLAM takes as input the empty set of effects and preconditions, while at the successive runs, it takes as input the action model learned during the previous run. We evaluated the performances of OLAM by means of precision and recall measures. This table summarizes the effectiveness of OLAM by comparing the action model learned with respect to the ground truth one. On the first column, there are the domain names. On the second column, the number of instances required to learn. So, for example, in the Barban domain, the action model learned in 4 instances is the same action model returned after 10 instances. The preconditions of the preconditions precision equals 1 in 5 out of 23 domains. That is, all unnecessary preconditions are removed, while in other domains is quite high, but does not equal 1 since there are some static predicates that are true in all states reachable from the initial one. So OLAM cannot reach a learning state to check whether these are really preconditions or not. The preconditions recall is always 1, and this is because the initial set of preconditions contain all the positive literals involving input operator object types. So there are no missing preconditions since the beginning. The positive effects are almost perfectly learned, except for the rover domain, and this is because rover contains some inconsistent effects which cannot be learned by OLAM. Similarly, for the negative effects, and the overall results are competitive, the precision is quite high, the recall is also almost always 1, and in the 5 out of 23 domains, the action model learned by OLAM on a single instance is exactly equal to the ground truth model. We have compared OLAM with FAMA, a state-of-the-art method for offline action model learning with partial observability. And for this experiment, we set FAMA for working in a fully observable environment, and we give as input to FAMA the same set of plan traces provided by its authors. These figures show the recall and precision of both OLAM and FAMA. OLAM achieves always better or equal precision and recall than FAMA. That is, OLAM learns more correct and complete action models than FAMA. Also in terms of efficiency, so the actions required by OLAM to learn the action models are less than the ones required by FAMA, except for the rover domain. And moreover, OLAM requires less time than FAMA to compute action models. So we have proposed an algorithm for online action model learning with full observability. OLAM selects the states to reach and actions to execute in order to acquire useful information about the operators. An implementation of OLAM shows some competitive results and that performs a state-of-the-art method for action model learning. And we also show some important theoretical properties of OLAM concerning the correctness and integrity of the learned models. OLAM works with full observability. In our future works, we would like to extend it to partial observability and continuous observations. Thanks for your attention.